going to continue with linear equations and functions and talk about how they relate to what is a function, what is not a function in this particular case. We'll start by identifying what a function is. This is the basic useful definition of a function, in that a function is a relation where each input has only one output. So if we were to use this as an example here, with this being an input, set of inputs, and this being the set of outputs, we'll give you an example of a function. Let's say our input values are 1, 2, 3, and 4. And then our output values were 10, 9, 8, 7. And this input 1 has an output of 10. This input 2 has an output of 9. This input of 3 has an output of 8. And this input of 4 has an output of 7. As you can see, each input, 1, 2, 3, and 4, has only one output. And that's 10, 9, 8, and 7 respectively. So each input has only one output. Let's compare that to what is not a function, and we'll label that as not a function. Again, we use the same setup here with the mapping. These are called mapping. Let's say I have 1, 2, 3, and again I have 10, 9, 8, and 7. And we take a look in here, and 1 goes to 10, so it has one output, and 3 goes to 7, it has one output, but we have 2, which goes with 8, as well as 9. So this input 2, right here, has more than one output, so it's not a function. Let me give you one more that is a function that sometimes confuses people just because it looks a little funny. Let's say we have 1, 2, we'll just use 3 this time. Let's say over here all we have is the number 10. Okay? And 1 has an output of 10, 2 has an output of 10, and 3 has an output of 10. 1 only has one output, 2 only has one output, and 3 only have one output. And you notice they only have one line coming out, so they are functions. That is a function there. All of these, the functions and the ones that are not functions, can be written as ordered pairs, as a table of values. They can be graphed. Your input are x values. Your output are y values. Okay? So that's something to keep in mind, because we can put these in multiple different forms, and you'll be able to do that. But this is a nice way to introduce it to you. Another way, if you're just given a graph to identify if something is a function or not, is to see if it passes what's called the vertical line test. What this says is the relation to the function if and only if no vertical line passes through 2 or more points on the graph. So I'll give you an example of something that is a function. That right there would represent a function, because if I take any vertical line, I'll use a couple of red vertical lines here, that vertical line only intersects at one point, right here. 1 point and 1 point only. Let's come over here. Again, this vertical line, only 1 point. We'll do one more. Come all the way out here. Again, another vertical line that intersects at only 1 point. So if you notice that that vertical line only crosses once, those are functions. Sometimes to understand what is a function, it helps to see what is not a function based on a graph. And we'll take a look at not a function now. Let's say we had something that was graphed that looks like this. Now I'll take a vertical line, this vertical line right here, and that vertical line crosses once, and it crosses our curve twice. So that fails the vertical line test right there. Obviously, we see on out it will also fail the vertical line test. We only need to show that it fails it in one spot, and that just happens to be the one we used for this example. So it crosses twice. It's not a function. Function notation is where we see f of x equals 2x minus 3. That f right there signifies function notation for us. So we have f of x equals 2x minus 3. As it says here, the f is simply the name of the function. F of negative 2 means to evaluate the function at negative 2. Before, we would have given you something like y equals 2x minus 3, and say evaluate that when x equals negative 2. Well, we're doing the same thing here. For example, let's use f of negative 2. So f of negative 2 in this case means everywhere we see x, we substitute in negative 2. So I have 2 times negative 2 minus 3. Now we simplify. We don't do anything with the left side. We do nothing with that. 2 times negative 2 is negative 4 minus 3. Negative 4 minus 3 is negative 7. So f of negative 2 is negative 7. So if we wrote that as an ordered pair, we have negative 2 as our x and negative 7 as our y value, our input and our output. We'll do one more here. Let's do f of, I don't know, f of 8. So again, everywhere we see x in our function, we substitute in 8. I have 2 times 8 minus 3. 2 times 8 is 16. We have 16 minus 3. That's 13. So if we were to write this as an ordered pair, it would be 8, comma, 13. Input 8, output 13. Again, please notice we're doing nothing with the f of negative 2 and the f of 8 other than that first step when we write it down. The last thing we'll be asked to do is to graph these. And now this really isn't anything new. It's actually, I think you'll find it to be the easiest of the new things that you learn because it is the most similar to something we've already done. We think of y equals negative 1/2 x plus 3. That's what's called slope-intercept form. This is still at slope-intercept form here and here. So again, this 3 is our y-intercept. This negative 1/2 is our slope. So we have everything that we need to graph. We start by plotting our y-intercept, going up 1, 2, 3, and plotting it at 0, 3 on our y-axis. Our slope is negative 1/2. That's down 1, right 2. So down 1, right 2. I can continue doing that all the way there. And our line would look like that. Again, same as we would in slope-intercept form. We'll start tomorrow's class by practicing several of these. I think, again, the slope-intercept form is essentially the same as what you've been doing, and it'll be relatively straightforward for you. The other stuff we'll pick up on. It's been done pretty well in the past, and I'm sure it'll be no problem for you as well. We'll see you tomorrow.